Okay, so let's look at example number 3. It's asking us to find the volume of a solid formed by revolving a region bounded by the graphs of y equals the square root of x and y equals x squared, and we're revolving it around the x-axis. Okay, so what you might want to do, if they don't give you a picture, and a lot of times they will not give you a picture, is to draw a picture of these two graphs so you can kind of visualize what's going on. Okay, we have the equation y equals square root of x. If x is 0, then y is 0. If x is 1, then y is 1. If x is, what? Can we do 4? 2, 3, 4. Then y is 2. And so our square root graph, zoomed in, kind of looks like that, right? And then we have a y equals x squared graph, a parabola, where if x equals 0, then y equals 0. If x equals 1, then y equals 1. If x equals 2, then y equals 4 way up here. And so my parabola graph kind of goes, shoots up like that, right? And so I'm looking for the area here. And I'm taking this solid and I'm revolving it around the x-axis. So if this is my x-axis and I take this little sliver and I revolve it around, what's going to happen to my shape? I'm a horrible artist, so if you look over here, that's kind of what the shape's going to look like. It's going to kind of look like a cone or like a contact lens, maybe something like that, right? But there's going to be a hole in it, so that when I end up slicing these into little pieces, I'm going to end up with a washer instead of a disc, or a donut instead of a cylinder, right? And so if I'm trying to find the volume of the revolution, I need to integrate it, but I need to be careful of doing my volume or my area underneath because there is a hole in my solid, okay? So let's first figure out our limits. We need to first figure out our limits by figuring out where these two graphs intersect each other. When we graphed it, we notice that they intersect each other here at 0, and they intersect each other here at 1. So I'm integrating it. If I'm revolving it around the x-axis, my little rectangles are perpendicular to the x-axis, so they're vertical. And so I'm integrating it from 0 to 1. So these are my limits, my x limits, from 0 to 1. Okay? Then I've got to figure out what my two radiuses are. Because I have, or my two radii, because I have a hole in my picture, I need to do my big radius minus my little radius. Okay? Don't forget your pi out in front, because we're going to do pi r squared. We're going to do pi big R squared minus pi little r squared. If I GCF out that pi, then I have a pi in the front. So we've got to figure out what our big radius is minus what our small radius is. So remember, our radius goes from the axis of revolution up to the very top of my solid. So what function goes from the bottom up to this line right here? Because here to here would be my radius. So what would be my radius? What function corresponds from the center up to the top? Isn't that the square root of x graph? So my big radius is the square root of x. Don't forget to square it because it's big R squared. Minus my little radius. Okay? If you look, my little radius is going to be from my axis of revolution, from the center to the bottom of my function. What function corresponds to the bottom of the from the x-axis up to the bottom of your function? That corresponds to your parabola, doesn't it? Your x squared. So if I take this x squared and then I square it, that would be my little radius. So I have my pi big R squared minus pi small r squared, and that's going to give me my volume of this solid when I rotate it from 0 to 1. Okay? If you look at this first part, when I go to integrate it, the x and the square root and the square ends up canceling each other out, and I'm just left with an x. What is x squared squared? Doesn't that turn into an x to the 4th? Don't forget about your pi in the front, and we're still integrating it from 0 to 1. So when I go to integrate, what is the integral of x? I've got my x squared over 2. What is the integral of x to the 4th? Well, I have x to the 5th over 5. And I'm integrating it from 0 to 1. Don't forget about your pi in the front. Okay? If I use my fundamental theorem of calculus and evaluate, I plug in my 1 and I get 1/2 minus 1/5 minus 0. And don't forget again about your pi in the front. Getting a common denominator for doing this without a calculator would be 10. This would be 5/10, this would be 2/10. So my final answer would be 3 pi over 10. So the volume of the solid that we would get when we rotate those two functions around the x-axis, so the volume of this little contact lens ends up being 3 pi over 10. Okay? So again, let's walk back through one more time what we had to do. I first graphed the picture so I can kind of visualize what's going on. I had to then figure out what my two intersections were. If you can't tell by graphing, then you have to set them equal to each other. I had to visualize what was going to happen when I rotated that around the x-axis. I figured out that there was going to be a hole in my little slices, so they were going to be washers. So I had to do pi big R squared minus pi small r squared. I had to figure out what my big radius was from my axis of revolution up to the very top of my function. I had to figure out what my small radius was from my axis of revolution up to my bottom of my function, and then I needed to integrate it. Okay? All right, let's do another one. So here's example number 4. Okay? And in all the examples we've done so far, we've been revolving around a horizontal axis with respect to x, right? Our axis of revolution has been horizontal, and our little rectangles have been vertical. So we've been integrating with respect to x. Well, what about this example? What if I gave you this example? It says find the volume of a solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1, and we want to revolve it around, this time, the y-axis. Okay, what do you think we should do first? I suggest we draw a picture. So let's draw a picture of what all this stuff would look like. Okay? Because this time they don't give us a picture. Let's start with my y equals x squared plus 1 graph. Isn't that a parabola? And that's a parabola starting up at 1. So if this is 1, then my parabola looks kind of something like this, right? What if x was 1? If x was 1, what's 1 squared? 1 plus 1 is 2. So that's 2. This is 1 and this is 2. And these are my two kind of guide points. Okay? All right, what does the line y equals 0 look like? Isn't the line y equals 0, isn't it this horizontal line that goes like that? So I've got this graph, I've got this graph, I've got a line x equals 0. X equals 0 would be this vertical line, x equals 0. And then I also have the line x equals 1. Okay? So if I'm looking at the area in between all those functions, I'm looking at this little piece right here. Okay? Okay? When I revolve this one, let's think about where I'm revolving it and how I'm revolving it. I'm revolving it this time around the y-axis. So this line is my axis of symmetry, and I'm revolving it in this direction. So when I revolve it, I'm going to end up with a shape that looks like this, right? Okay, so kind of visualize that. Again, I'm not the best artist, so kind of visualize what it would look like if I kind of spun it around. This problem's a little bit different, because look from 0 to 1 on the line. Look at this piece right here. If I was just looking at that piece, and I was revolving that piece around the y-axis, and I took little slices, and now I'm going to slice horizontally, right? So because my axis of revolution is the y-axis, and I want to be perpendicular to my axis of revolution, my little rectangles are going to be horizontal this time. If I were to slice it, would those slices have holes or no holes? Would those be discs or would those be washers? Wouldn't they be discs? There'd be no holes there? If, again, I was just looking from 0 to 1 on the y, if I were to slice them into little slices, they would be discs, not washers. Okay? But look from 1 to 2. If I'm looking at this piece from 1 to 2, and I revolve it around the y-axis, and I have my little rectangles inside here, and I revolve those around the y-axis, are those going to be discs or are those going to be washers? Aren't those now going to have holes? So what do you think we have to do in this problem? We're going to have to set up two different integrals, right? We're going to have to set up an integral from 0 to 1 on the y, and then we're going to have to set up an integral from 1 to 2 on the y using two different methods. We're going to have to use the disc method here, and we're going to have to use the washer method here. We're going to have to use two different methods here. So are you ready? All right. And remember, we're doing it with respect to y. My little rectangles are going to be horizontal now, so we're not doing it with respect to x, we're doing it with respect to y. Let's go ahead and set up our two different integrals. Okay? Let's start with the first one. Let's do from 0 to 1. These are y limits. If we're doing the disc method, then remember we're doing pi r squared h. I'm going to bring the pi out in front. I need to figure out what my radius squared is, and then my little heights, remember, are not dx's, remember, but they're dy's because my rectangles are sideways. Okay? So looking back at my picture, if I want to figure out what my radius is, picture's getting a little crazy here. If I want to figure out what my radius is, I need to go from the center, my axis of revolution, out to the very end of my disk, out to the very end of my function. Well, what is this amount? This isn't my parabola, remember. This is my line at y equals what? Or at x equals what, I should say. At x equals 1, isn't it? Okay? So my radius is that far. No matter where I'm at in this little piece, isn't my radius always going to be 1? Until I get a little bit farther. But we're only looking from 0 to 1. Isn't my radius always 1? It's 1 unit long. So my radius is going to be 1. Remember to square it because you're doing r squared. Okay? All right, let's do our second integral. And let's do the washer part here. The washer part is the part from, what did we say, 1 to 2 on the y? So we're going to go from 1 to 2. Remember the washer method is when we have a hole in it, where we have to do pi big R squared minus pi little r squared. Okay? They both have pi's in them, so can I take the pi out? And now we just have to figure out what our big radius is minus what our small radius is. Remember, we're doing it with horizontal rectangles, so we're doing it with respect to y. Okay? So let's figure out, going back to our picture, what our big radius is and what our small radius is. Okay? I can change the color here. I've got so many colors. Can I do, how do I change my color? What would show up good? Yellow? Let's try yellow. Well, that didn't work. Oh. Why didn't that work? Ooh, there it goes, but I don't know if it's easier to see or not. Okay, we'll try yellow. All right, so if I'm looking for big radius and small radius, remember I'm looking in this little piece right here, and I want to revolve it around the y-axis. So if I'm revolving it around the y-axis, I need to go from my axis of revolution out to the very end. Axis of revolution out to the very end. Axis of revolution, out to the very end. No matter where I drew my little rectangle, how long was that radius going to be? How long was it going to be from my axis of revolution out to the end? Wasn't it going to be 1 again? So my axis of revolution to the end of my function, my big radius, was going to be 1. Now let's figure out what the small radius is. My small radius, let's see if I can change to a different color. What color have we not used? Can I use this, maybe this blue? Woo! I don't know if that's going to show up either. I don't know, we'll try. All right, if I use my small radius is from my axis of revolution to the inside. My axis of revolution to the inside. And doesn't that inside correspond to my parabola? However, isn't my parabola in terms of x's? And I want it in terms of y's, don't I? So how would I get this equation to be in terms of y's instead of x's? Couldn't I resolve? Couldn't I take this and get the x by itself instead of the y by itself? So subtract 1, square root both sides, and you get x equals the square root of y minus 1. So that corresponds to my little radius from the axis of revolution to my function would be the square root of y minus 1. I've got my big radius and I've got my little radius. Okay? All right, so now we just have to integrate these two things and then add them together. All right? So what is 1 squared? 1, what is the integral of 1? Just y? So I have y from 0 to 1. Don't forget your pi out in front. So I end up getting 1 pi minus 0 pi. Okay? Plus, I want to add it over here. 1 squared is 1. What happens here with the square root and the square? Don't they cancel each other out? And I'm left with negative y plus 1 if I distribute the negative through. All right, integrating that little piece, I get y minus y squared over 2. Oh wait, can I just add those two together? Could I do that? The two ones? And then integrate it and I get 2y. Can I do that? From 1 to 2, and don't forget about your pi out in front here. If I plug in my 2, I get 4 minus 4 squared, or 2 squared is 4 divided by 2 is 2. Minus, if I plug in my 1, I get 2 minus 1/2. Correct? I get 2 minus 1/2. Isn't that 1/2? Don't forget about your pi. So I get a pi over 2 here. And I have my pi over here. So now if I add them together, I get 3 pi over 2. So the area, the volume, excuse me, of the solid, when I rotate it around the y-axis, is 3 pi over 2. Okay? Draw your picture, find your limits, figure out which direction your rectangles are. Are they vertical or horizontal? You've got to figure out then, are you using the disc method or the washer method? Do you have a hole or no hole? And then set up your integrals. Okay? We will start tomorrow probably with a few more examples, because they are a little bit different always, no matter what problem you're doing. They're always a little bit different than each other. So we'll practice a little bit more tomorrow. I would like you to do your best to start looking over the homework. It's 7.2a on page 463. We're doing 11 through 35, every other odd.